Maggie, when it comes to mind, we think comfort food when everything else is letting you down. You at least have a bowl of Maggie. The food you eat when you need a break of any sorts. Interestingly, Maggie can even be part of chemistry, the science kind, not just the chemistry between yourself and your bowl of Maggie at 2 a.m. in the morning. You might be wondering, how is this possible? Let's take a small detour to our fellow friends' endothermic and exothermic reactions. First up, we have an endothermic reaction, which is a reaction that absorbs heat from its surroundings. Simply put, an equation for this would be reactant plus heat gives you your products. Examples would be ice melting and cooking, but we'll get back to the cooking concept later. Next up, we have an exothermic reaction, which is a reaction that releases more heat than it absorbs. Simply put, it can be described as a reactant that gives off a product and heat. Example could be combustion. Now you can see a pan full of water that is in the process of boiling. Now it is boiled and I am adding Maggie to it. Boiling is an endothermic process because it requires more heat than it gives off. Now I'm adding magic stuff to it. It's formed and I'm putting a fork into it for embellishment purposes. As mentioned before, cooking is an endothermic process because it requires more heat than it gives out. We can see that in the cases of boiling water, cooking an egg, and even cooking Maggie. Specifically in the case of Maggie, Maggie is composed of multiple starch molecules, one of which is amylose, which changes their molecular structure in the presence of heat. This addresses why cooking Maggie is endothermic because it requires the heat to change the structure and it doesn't release much heat in return. This happens at a fixed temperature and explains why Maggie is hard and brittle before cooking and becomes soft and more noodle-like after cooking.